Hello friends, to this point of discussion in thermodynamics, we have focused our attention on the first law of thermodynamics, which requires that energy be conserved during a process. In today's lecture, we introduce ourselves with the second law of thermodynamics, which asserts that processes occur in a certain direction and that energy has quality as well as quantity. A process cannot take place unless it satisfies both the first and second law of thermodynamics. The objectives of this discussion would be to introduce the second law of thermodynamics, identify valid processes as those that satisfy both the first and second law of thermodynamics, discuss thermal energy reservoirs. Introduction to the second law. In the earlier lectures, we applied the first law of thermodynamics or the conservation of energy principle to processes involving closed and open systems. It was pointed out repeatedly in those lectures that energy is a conserved property and no process is known to have taken place in violation of the first law of thermodynamics. Therefore, it is reasonable to conclude that a process must satisfy the first law to occur. However, satisfying the first law alone does not ensure that the process will actually take place. As this example here explains that it is a common experience that a cup of hot coffee left in a cooler room eventually cools off. This process satisfies the first law of thermodynamics, since the amount of energy lost by the coffee is equal to the amount gained by the surrounding air. Now let us consider the reverse process, the hot coffee getting even hotter in a cooler room as a result of heat transfer from the room air. We all know that this process never takes place, yet doing so would not violate the first law as long as the amount of energy lost by the air is equal to the amount gained by the coffee. In another familiar example, consider the heating of a room by the passage of electric current through a resistor. Again, the first law dictates the amount of electric energy supplied to the resistance wires to be equal to the amount of energy transferred to the room air as heat. Now let us attempt to reverse this process. It will come as no surprise that transferring some heat to the wires does not cause an equivalent amount of electric energy to be generated in the wires. Finally, consider a paddle wheel mechanism that is operated by the fall of a mass. The paddle wheel rotates as the mass falls and stirs a fluid within an insulated container. As a result, the potential energy of the mass decreases and the internal energy of the fluid increases in accordance with the conservation of energy principle. However, the reverse process, erasing the mass by transferring heat from the fluid to the paddle wheel, does not occur in nature, although doing so would not violate the first law of thermodynamics. It is clear from these arguments that processes proceed in a certain direction and not in the reverse direction. The first law places no restriction on the direction of a process, but satisfying the first law does not ensure that the process can actually occur. This inadequacy of the first law to identify whether a process can take place is reminded by introducing another general principle, the second law of thermodynamics. The use of the second law of thermodynamics is not limited to identifying the direction of processes. However, the second law also asserts that energy has quality as well as quantity. The first law is concerned with the quantity of energy and the transformations of energy from one form to another with no regard to its quality. Preserving the quality of energy is a major concern to engineers, and the second law provides the necessary means to determine the quality as well as the degree of degradation of energy during a process. As shall be discussed, more of high temperature energy can be converted to work, and thus it has a higher quality than the same amount of energy at a lower temperature. The second law of thermodynamics is also used in determining the theoretical limits for the performance of commonly used engineering systems such as heat engines and refrigerators, as well as predicting the degree of completion of chemical reactions. Thermal energy reservoirs. In the development of the second law of thermodynamics, it is very convenient to have a hypothetical body with a relatively large thermal energy capacity that can supply or absorb finite amounts of heat without undergoing any change in temperature. Such a body is called a thermal energy reservoir or just a reservoir. In practice, large bodies of water such as oceans, lakes and rivers as well as the atmospheric air can be modeled accurately as thermal energy reservoirs because of their large thermal energy storage capabilities or thermal masses. The atmosphere, for example, does not warm up as a result of heat losses from residential buildings in winter. Likewise, megajoules of waste energy dumped in large rivers by power plants do not cause any significant change in water temperature. Another familiar example of a thermal energy reservoir is the industrial furnace. The temperatures of most furnaces are carefully controlled and they are capable of supplying large quantities of thermal energy as heat in an essentially isothermal manner. Therefore, they can be modeled as reservoirs. A body does not actually have to be very large to be considered a reservoir. Any physical body whose thermal energy capacity is large relative to the amount of energy it supplies or absorbs can be modeled as one. The air in a room, for example, can be treated as a reservoir in the analysis of the heat dissipation from a TV set in the room, since the amount of heat transfer from the TV set to the room air is not large enough to have a noticeable effect on the room air temperature. A reservoir that supplies energy in the form of heat is called a source, and the one that absorbs energy in the form of heat is called a sink. Thermal energy reservoirs are often referred to as heat reservoirs since they supply or absorb energy in the form of heat. Heat transfer from industrial sources to the environment is a major concern to environmentalists as well as to engineers. Irresponsible management of waste energy can significantly increase the temperature of portions of the environment, causing what is called thermal pollution. If it is not carefully controlled, thermal pollution can seriously disrupt marine life in lakes and rivers. Heat engines. As discussed earlier, work can easily be converted to other forms of energy, but converting other forms of energy to work is not that easy. The mechanical work done by the shaft, for example, is first converted to internal energy of the water. This energy may then leave the water as heat. We know from experience that any attempt to reverse this process will fail. That is, transferring heat to the water does not cause the shaft to rotate. From this and other observations, we conclude that work can be converted to heat directly and completely, but converting heat to work requires the use of some special devices. These devices are called heat engines. Heat engines differ considerably from one another, but all can be categorized by the following. They receive heat from a high temperature source, solar energy, oil furnace, nuclear reactor, etc. They convert part of this heat to work, usually in the form of a rotating shaft. They reject the remaining waste heat to a low temperature sink, the atmosphere, rivers, etc. They operate on a cycle. Heat engines and other cyclic devices usually involve a fluid to and from which heat is transferred while undergoing a cycle. This fluid is called the working fluid. The term heat engine is often used in a broader sense to include work production devices that do not operate in a thermodynamic cycle. Engines that involve internal combustion, such as gas turbines and car engines, fall into this category. These devices operate in a mechanical cycle but not in a thermodynamic cycle, since the working fluid, that is, the combustion gases, does not undergo a complete cycle. Instead of being cooled to the initial temperature, the exhaust gases are expelled and replaced by fresh air and fuel mixture at the end of the cycle. The work producing device that best fits into the definition of a heat engine is the steam power plant, which is an external combustion engine. That is, combustion takes place outside the engine and the thermal energy released during this process is transferred to the steam as heat. This is a rather simplified diagram of the actual steam power plant. The various quantities shown on this figure are as follows. Qin is the amount of heat supplied to steam in boiler from a high temperature source, maybe a furnace. Q out is the amount of heat rejected from steam in condenser to a low temperature sink. W out is the amount of work delivered by steam as it expands in turbine. W in is the amount of work required to compress water to boiler pressure. Notice that the directions of the heat and work in directions are indicated by the subscripts in and out. Therefore, all four of the described quantities are always positive. The net work output of this power plant is simply the difference between the total work output of the plant and the total work input, that is, W net out is equal to W out minus W in. The net work can also be determined from the heat transfer data alone. The four components of the steam power plant involve mass flow in and out, and therefore they should be treated as open systems. These components, together with the connecting pipes, however, always contain the same fluid. No mass enters or leaves this combination system, which is indicated by the shaded area. Thus, it can be analyzed as a closed system. Recall that for a closed system undergoing a cycle, the change in internal energy delta U is 0, and therefore the net work output of the system is also equal to the net heat transfer to the system, that is, W net out is equal to Q in minus Q out. Thermal efficiency. In equation W net out is equal to Q in minus Q out, Q out represents the magnitude of the energy wasted in order to complete the cycle, but Q out is never 0. Thus, the net work output of a heat engine is always less than the amount of heat input. That is, only part of the heat transferred to the heat engine is converted to work. The fraction of the heat input that is converted to net work output is a measure of the performance of a heat engine and is called the thermal efficiency eta Th. For heat engines, the desired output is the net work output and the required input is the amount of heat supplied to the working fluid. Then the thermal efficiency of a heat engine can be expressed as net work output divided by total heat input, or eta Th is equal to W net out divided by Q in. It can also be expressed as eta Th is equal to 1 minus Q out over Q in, because W net out is equal to Q in minus Q out. Cyclic devices of practical interest such as heat engines, refrigerators and heat pumps operate between a high temperature medium or reservoir at temperature Th and a low temperature medium at a temperature TL. To bring uniformity to the treatment of heat engines, refrigerators and heat pumps, we define two quantities, Th and Ql. Th is the magnitude of heat transfer between the cyclic device and the high temperature medium at temperature Th. Ql is the magnitude of heat transfer between the cyclic device and the low temperature medium at temperature TL. Notice that both Ql and Qh are defined as magnitudes and therefore are positive quantities. The direction of Qh and Ql is easily determined by inspection. Then the net work output and thermal efficiency relations for any heat engine can also be expressed as W net out is equal to Qh minus Ql and eta Th is equal to W net out divided by Qh, or eta Th is equal to 1 minus Ql upon Qh. The thermal efficiency of a heat engine is always less than unity, since both Ql and Qh are defined as positive quantities. Thermal efficiency is a measure of how efficiently a heat engine converts the heat that it receives to work. Heat engines are built for the purpose of converting heat to work, and engineers are constantly trying to improve the efficiencies of these devices, since increased efficiency means less fuel consumption and thus lower fuel bills and less pollution. The thermal efficiencies of work producing devices are relatively low. Ordinary spark ignition automobile engines have a thermal efficiency of about 25%. That is, an automobile engine converts about 25% of the chemical energy of the gasoline to mechanical work. This number is as high as 40% for diesel engines and as high as 60% for large combined gas steam power plants. Thus, even with the most efficient heat engine available today, almost one half of the energy supplied ends up in the rivers, lakes or the atmosphere as waste or useless energy. So friends, here we come to the end of our discussion and therefore we sum up. The second law of thermodynamics states that processes occur in a certain direction, not in any direction. A process does not occur unless it satisfies both the first and the second law of thermodynamics. Bodies that can absorb or reject finite amounts of heat isothermally are called thermal energy reservoirs or heat reservoirs. Work can be converted to heat directly, but heat can be converted to work only by some devices called heat engines. So that is it for today. In the next lecture, we shall be discussing Kelvin Planck's statement, refrigeration and heat pumps. Thank you very much.